Today we are going to discuss random access memory, also known as RAM. It is a semiconductor memory and it uses either positive feedback or capacitive charge to store the information. RAM is a read-write memory and it allows writing of data bits in the memory array as well as reading of stored data bits. The main characteristics of RAM is that any cell in the memory array can be accessed with nearly equal access time. Based on the operation type of data storage cells, RAM are classified into two categories: static RAM, that is SRAM, and the dynamic RAM, that is DRAM. Static RAM stored information depends on the state of transistor, whether transistor is on or off, and it requires continuous power supply. Whereas dynamic RAM stored information depends on the charge in capacitor and it does not require a continuous power supply, but the charge in the capacitor must be refreshed after a particular interval of time. In this presentation, we will see one transistor dynamic RAM. Before starting the discussion on 1T DRAM, let us discuss a general architecture of RAM. We require a row decoder. It is having n input and hence it will have 2 to the power n output. It is an active high decoder. Similarly, we require a column decoder. It is having m inputs and hence 2 to the power m output. It will give total 2 to the power m into 2 to the power n address. On each address, there is a DRAM cell. Depending on the output of row decoder and column decoder, a particular DRAM cell can be selected to read or write the information. Now we will see the structure of 1T DRAM. We require a word line which is the output of row decoder. Whenever we want to read or write data, word line must be high. Next, we require a bit line which is the output of column decoder. To write any data, data is supplied through bit line, and to read any data, data is read through bit line. Then we require one n-channel MOSFET. The gate of n-channel MOSFET is connected to the word line and the drain of n-channel MOSFET is connected to the bit line. We require one cell capacitor which is responsible to store the information. The bit line capacitance is represented by capacitor CB. Now we have two capacitors CB and CC. Let us assume that MOSFET is acting as a on switch. The given diagram will be CB and CC are connected in parallel. Let us assume that we have stored some information in CC, and when we switch on the MOSFET and we connect CB and CC in parallel, will it affect the stored data? That we will see next. Now we have two capacitors CB and CC. The voltage across CB is given by VB and voltage across CC is given by VC. VB is given as QB by CB, where QB is charge stored in the CB. Similarly, the Vc is given by Qc by Cc. Now let us assume that we connect these capacitors by switching on the MOSFET. The final voltage Vf is given by Qb plus Qc divided by Cb plus Cc. Now the difference in the bit line voltage delta Vb is equal to Vb minus Vf, which can be find out using the given calculation. Once we have a delta Vb, that is equal to Cc into Vb minus Vc divided by Cb plus Cc. Now let us assume Vb is equal to 2.5 volt, Vc is equal to 5 volt, Cv is equal to 1 picofarad and Cc is 50 femtofarad. If we want to calculate the delta Vb, it is equal to 119 millivolt, which is very less. When we calculate final voltage after connecting both the capacitors, we get either 2.38 volt or 2.61 volt. In both the cases, it is neither logic 0 nor logic 1. Therefore, we can say that while reading, we have destroyed the data. We will see an scheme how to overcome this problem. Figure shows the basic bistable memory element. Alternatively, we can say that we have two CMOS inverter. The output of one CMOS inverter is connected as an input to the other CMOS inverter. We assume that both the CMOS inverters are operating at their logic threshold, means Vout1 is equal to Vout2 is equal to 0.5 VDD. Now, if we will see the plot, as we increase the Vout2, Vout1 decreases. Similarly, the input is taken on y-axis. As we increase the Vout1, the Vout2 decreases. If we superimpose both the plot, we are going to get the butterfly diagram, and we are operating at 0.5 VDD, that is a logic threshold of both the inverters. Now let us assume that we increase Vout by 119 millivolt. So now we have a Vout is equal to 2.61 volt. As Vout1 increased, the Vout2 will decrease. As Vout2 decreases, the Vout1 will further increase, and finally Vout1 is going to settle at VDD and Vout2 is going to settle at 0 logic. This is a very important concept. We are going to use this to explain the non-destructive reading technique of 1T DRAM. The given figure shows the sense amplifier. It is very similar to bistable memory element which we have discussed in the previous slide, except the transistor with gate terminal connected to S. If S is low, the pull down network of both the inverters are not connected to ground terminal, and hence this device will not be active. If S is equal to 1, it is going to work as a basic memory element. The given figure shows a column of DRAM. Let us assume that in a given column we have total 32 cells. So first 16 cells are going to be located above the sense amplifier. The second set of 16 cells are going to be located below the sense amplifier. The bit lines are shown in the figure. The sense amplifier, which is made of two inverters connected back to back, is shown in the figure. Now, let us assume that in a given cell, 5 volt information is stored. When we make the respective word line high, this is going to change the bit line voltage, which was pre-charged to 2.5 volt, because the voltage stored in the cell capacitance is 5 volt. So the new voltage of the upper bit line is going to be 2.61 volt, which is larger than the 2.5 volt, which is the lower bit line voltage. Now these we are going to make Rs is equal to 1. When we make Rs is equal to 1, both the bit lines will be connected to the sense amplifier. It will take the above bit line to 5 volt and below bit line to 0 volt, which already we have seen in the previous discussion. So in this process, while reading the information, we are also writing the information in the respective cell. Now to get the output, we make Cs is equal to 1, which is a control signal which connects the bit line to the output line. Now we will discuss write and read operation of 1T DRAM. To access the storage capacitor, we use word line. Word line must be high to access the capacitor, and we used to read or write the signal using the bit line. So, write operation. 1T dynamic memory cell consists of a capacitor Cc, which can be charged from read write line, that is bit line, provided that the word line is high. Read operation. The state of charge across Cc can be read via the same read write line, that is a bit line, with a high word line. Hence, during read operation, a sense amplifier is used to differentiate between a stored 0 and stored 1. Thank you.